Awesome. Okay. So as I said in my email this weekend, I went ahead and attached the last 2 weekly plans so that you've got everything. We are working off of the same set of notes today, Thursday, and next Tuesday. So once you print those out, you're good. You don't need any other documents. There are 6 sections on those notes. We will do 2 sections today, 2 sections on Thursday, and 2 sections next Tuesday. The video for this week covers the 4 sections that we're going to cover this week. And then the video for next week covers what's going to be on Tuesday. So that's kind of like the end of everything. And I'll go over a little bit more at the end of class, like what the specific assignments are. Okay. So the first thing I want to talk about is looking at our periodic table. What element do we actually think is the biggest element on this periodic table? So where do you think the largest element in sheer physical size actually is? The left, the right, the top, the bottom? What do we think?
The bottom.
It's going to be on the bottom, absolutely. So that makes a lot more sense. But we've got different places on the bottom. So do we think that, the biggest element is going to be down here on the bottom left or down here on the bottom right?
It's the bottom right.
You would think it's the bottom right, wouldn't you? Because that's where the largest atomic numbers are. But it is not. The biggest element is actually francium down here on the bottom left, which has a much smaller atomic number than oganesson, which is over here on the bottom right. So that's part of the reason why I want to go through these specific notes, because if we were just left to our own intuition, we would assume that the biggest element is the one with the biggest atomic number. And that is wrong. And we're going to explain why today. So switching over then. So the notes look like this. They are horizontal because that was the easiest way to get the images in there. So notes on periodic trends. Like I said, it was on the participation assignment in Google Classroom. 2 sections each of the next 3 days. So let me switch over. Yes, no? Do we not want to? There we go. Okay. So, believe it or not, I actually had a lot of fun making these notes because I got to find all sorts of colorful pictures, because I don't normally get to use colorful pictures because I don't have a color printer. But if we're doing things this way, I can use all the color I want. Okay. So the only difference is, since it's horizontally arranged, I don't quite get to zoom in as much as I normally do. What's that? Okay. Okay, what? Sorry, I just letting some more people into class before I get started.
Morning.
Morning. Okay. All right. So to begin with, when discussing any periodic trend, one of the things you have to be really, really careful about is how you actually do any sort of written explanation. So when you are discussing a periodic trend, you have to be able to separate what you observe from what explains it. So some questions just ask for a straight observation. Which one is bigger? Which one is smaller? But some questions ask for an explanation of why is this one bigger? So you have to make sure that you're answering the question that they ask. So if they ask for an observation, give an observation. But if they ask for an explanation, then make sure you are actually providing an explanation. So a trend can be observed that says the bigger atoms are at the bottom of a group, but that is not an explanation. So on the assignment for this week and next week, I do give you some pointers about what needs to be in an actual explanation. And I'm going to say the same thing right here. An explanation must include a discussion of either distance or nuclear charge. That is kind of why we spent that time last week talking about those things. So you have to describe either the distance or the nuclear charge, what that means for the Coulombic attraction, and then how that attraction determines the trend. So what you're going to find as we go through these notes is that's how I've laid out each sort of explanation. So I have provided model explanations in these notes for you to pattern your answers after. Okay, so we're going to start with atomic radius, because atomic radius is basically distance or size, and therefore it does kind of affect or determine all of the other things we're going to cover. So the definition for atomic radius, atomic is telling you it's about the atom, and radius should be telling you it's a distance of some sort. So it is the distance, instead of the center of a circle, the center of our atom is the nucleus. And instead of going from the center of a circle to the edge of the circle, well, the edge of our atom is the electron cloud. But for all practical purposes, that means to the valence electrons. So our atomic radius is the distance from the nucleus to the valence electrons. Okay, so if you look at this graph, all right, at this image, the largest element is down here, and that largest element is francium. And while it can be kind of hard to tell in this image, and it also depends on whose measurements you're looking at, the smallest element is typically considered to be helium. These are opposite places. So remember that we're either going to have things in this bottom left zone, or we're going to have things in this bottom right. I mean, this top right, because our attractions, that's where we have either low attraction, right? Or up here we have high attraction. That's what we said last week. So looking at some actual explanations. So these are the observations. And down below, these are my two explanations. So first off, from left to right across a period, what is happening to the atomic radius as I'm going left to right across a period? Bigger or smaller?
Smaller.
Smaller. So atomic radius decreases. Now, did it decrease very much?
Kind of.
I mean, kind of, but you can see that like in the first couple of periods, it's a little bit more, but I mean, you can tell that this red one is bigger than this black one, but it's not like it changed a whole lot, but it does decrease. And the reason it decreases anytime we're talking about a period, the reason anything happens in a period is because of the nuclear charge. Okay, and remember that nuclear charge is essentially how many protons do you have? Okay, so we have more protons on the right-hand side. So our nuclear charge is increasing. but all of our valence electrons are entering the same shell or energy level. So if I'm putting all this stuff in the same energy level, but I'm increasing the amount of charge, I'm basically not changing my distance much, but I am increasing my charge. And so if I'm not changing distance, but I'm increasing charge, what's going to happen to my attraction? Increase or decrease? Johanna's not here to bail you guys out. Everybody else is going to have to answer for once.
Increase.
It's going to increase. All right, so the attraction is increasing. So if my attraction is increasing, that is literally pulling my valence electrons in, okay? So essentially, the way to look at this, on the left-hand side, I have very few protons in comparison to my number of valence electrons. On the right-hand side, I have a lot more protons in comparison to my valence electrons, and so therefore everything gets pulled in, gets pulled in, gets pulled in, and I get a little bit smaller. Now, top to bottom down a group is much easier to explain. So obviously, if I compare hydrogen up here to francium down here, clearly my atomic radius is increasing. And there is a very simple explanation. All of my valence electrons are going into a new electron shell. And remember, I have like one little shell here. I have two here. I have three here. I have four here, et cetera, et cetera. I get bigger and bigger. Every time I add in new shell, that shell is farther away from the nucleus. So farther away means more distance. More distance means my attraction does what? Increase or decrease?
Decreases.
Decreases. Okay, so if I am decreasing my attraction and my valence electrons are farther away, that means that I'm going to get bigger. But there's another thing at play here. You have to remember, and I'm just going to draw it down here. So if I have, say, potassium with 19 positive protons, and I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then one more, and I've got that. So these 19 protons are trying to attract this guy, all right? And that's my distance. However, all of these electrons here, if I have all those electrons, what does a whole bunch of electrons, what are they going to do to each other? Because they're all negative.
They're going to push each other away.
They're going to push each other away, okay? So all of these are pushing each other out. So not only do I literally have my valence electron in a farther circle, but I also have everything between that valence electron and the nucleus also pushing each other out. So with this extra bit of repelling, it makes me even bigger. So I have a much larger difference in distance and size going down a group than I do across a period, because I've got additional layers and I've got this pushing away. So that's the basics of atomic radius. But I do want to go into slightly more detail as we're talking about this going down a group, because on the exit ticket last week, we were about 50-50 split on talking about who had more attraction. And a lot of people thought that barium would have more attraction than magnesium. And it does not. Magnesium has a considerably larger amount of attraction, but you were just thinking about protons. So we need to dig a little bit closer here. And if we look at this, so this is a similar picture to what we were looking at last week, right? We've got lithium, sodium, and potassium. So when we move down a group, right, lithium has a 3+ charge, sodium has an 11+, because that's how many protons, and potassium has a 19. Okay, so there is increased nuclear charge going down the group. But that increased nuclear charge ends up getting canceled out by these circles. So it's canceled out by the layers of those complete electron shells. So the easiest way to think of this is like if you tried to put a magnet on your refrigerator, but first you wrapped that magnet in layers of cotton. It's not going to have as much attraction because you wrapped it in stuff. We are basically wrapping our nucleus, all that nuclear charge, with these red layers of full electrons, and they kind of cancel each other out. So these complete electron shells, these guys, right, the ones in red, are referred to as core. Right, they are core electrons because they're on the inside, right? Like an apple core is on the inside. So you need to think about core as being on the inside. And that is different from your little valence electron. Valence electrons are the ones on the outside. So core electrons are like our shielding or cotton, and valence electron is the thing we actually care about. So the core electrons provide what we referred to as shielding. They protect the valence electron from the attraction of the nucleus. And they do that because they repel against each other. And that increases that distance, as we said. So as you move down a group, you can see that this core gets bigger. And since the core gets bigger, our shielding, what we refer to as shielding, our shielding is also going to increase, as well as that literal physical distance. So this core versus valence is going to come back into play later on in these notes. But the way to think about it is, like in lithium, there's 2 electrons in that core. Those 2 negatives and those 3 positives, well, those 2 negatives cancel out 2 of those positives. That's how you can think about it. For sodium, if you counted up the dots, there's 10 electrons in that core, and those 10 electrons cancel out 10 of the protons, leaving you only a +1 trying to pull that valence electron. And for potassium, there's 18 electrons in that core that are canceling out 18 of the protons, leaving you with just 1 little proton trying to pull that 1 little valence electron. That's kind of how this core notion works. And another way to think about it is if you write out the electron configurations using that noble gas thing, right? Helium 2s1, and that would have been neon 3s1, and this would have been argon 4s1. And if you look at it this way, hey, the core is what we used to put in brackets. So it's all of these things are kind of connected. There's no one way to explain it. So like whichever framing kind of works in your head is totally fine. But that's what we got for atomic radius. So this explains why the bottom left-hand side is bigger because the left-hand side has less nuclear charge than the right-hand side. Hence, francium bigger than oganesson. So I'm going to scooch it up a little bit so we can look at the bottom of these. And we're going to talk about ionic radius. So ionic radius, well, it's not much of a difference in definition because it's basically the distance from the nucleus to the edge of the electron cloud, but instead of an atom, we're talking about an ion. The difference is we have two different types of ions. We have cations and we have anions, and they do different things because they're different types of ions. So which one of those is positive?
Cation.
Cations. And anions are negative. Okay, so did cations gain or lose electrons?
Lose.
They lose. All right, and anions gain. So without even thinking about it too much, if you lose an electron, do you think you get smaller or bigger?
Bigger.
Losing something makes you bigger here? For once, it's not opposite land. Losing actually is going to make you smaller, and gaining actually is going to make you bigger. For once, I'm not actually going to make things difficult. So if I'm losing electrons, I do get smaller. And if I gain, I do get bigger. For once, the words actually make sense. But if we look at the picture, it can make even more sense. So when I form a cation, I lose an electron. So you may not be able to see it here, but this is sodium. And sodium has 11 protons and 11 electrons. And when it forms a sodium plus, right, it forms a 1 plus, well, it does not change its number of protons, but it does lose an electron and become 10. So it's my valence electron that I lose. And when I pull this guy off, there is literally nothing else on this entire circle. So if I lose that electron, I literally lose that entire circle. I lose an entire valence shell. It is gone. There is nothing there. I have lost this entire ring, and therefore I am automatically smaller because I am one energy shell less. In addition, I now have 10 positive protons in the middle. 11 positive protons in the middle, but only 10 electrons outside. So who's got more pull there? The 11 in the middle or the 10 on the outside? Who can pull more? The 11 or the 10?
The 11.
The 11. So since the 11 is a bigger number, well, it also just kind of sucks everything in a little bit closer. So there's two reasons why we're going to get smaller. I lose a whole shell, and my 11 on the inside pulls everything in tighter. And it's the exact opposite when I make an anion. When I make an anion, so this is fluorine. All right, so I have 9 protons and 9 electrons. And when I become the ion, I'm still 9 protons, but I gain an electron, and I'm now 10. So there's an empty space when you make an anion that the electron fills into. But now, if you think about it, I've got 9 in the middle, but I've got 10 on the outside. So who do I have more of? I have more on the outside, so everything kind of pushes out. And the way to think about it is this extra electron repels away from all the others, and it makes me a little bit bigger. So that's kind of some little bit of basic. If you need to, take a picture of that, and I'll switch to the last page of the notes. And really fast, let me just update attendance because I've been letting people in. Johanna's still taking her test. I still don't see Micaiah. Still don't see Shamir, who said he was going to prep for his test. I don't see Manny. I don't see Eliora or Dalia or Josh or Jayla or either Jada, unless I accidentally left you in. Okay.
Wait, I'm here.
Who is here?
Sophia.
Yeah, I didn't say your name. I saw you.
Okay, sorry.
Yeah, no, that's fine. Okay. So, this last set of notes. This little image here shows a comparison of what happens between the atom and the ion for each of these things. So, we'll look first at the cations. All right, so these are the cations over here. And these are the anions over here. So you can see that for all of them, my cation got smaller, right? When I became an ion, I got smaller, all of them. All of them got smaller. And it's really easy to imagine that when you take that electron off, it's like peeling away the layer of an orange to leave it smaller down underneath, okay? So removing an electron is pulling off that entire outer shell, and now it's gone. All of them. Every single cation gets smaller. There is no exception here. Every cation gets smaller. But on the opposite side, these anions, when I stick more electrons on, I always get bigger. I always get bigger. Every single time. I am bigger, I am bigger, I am bigger. Because I'm shoving more things around it. So cations will always become smaller than the original atom. Reasons. For most metal cations, when they become a cation, an entire shell is lost. And if you lose an entire shell, that means you are now going to decrease the distance from the nucleus to your valence electrons. And decreasing distance does what to your attraction? Increase or decrease?
Increase.
Increase, all right? Decreasing the distance increases the attraction, right? More attraction when you're close together. And if you increase the attraction, that pulls all the remaining electrons in closer. So that's pretty logical sense for the cations. But there is a special little case we do need to talk about, and that is those darn transition metals. So remember, the transition metals are all the ones we have to use the Roman numerals for, right? Iron 2 and iron 3, copper 1 and copper 2, lead 2 and lead 4. They have multiple different cations that they can make. So each electron that is removed will decrease the amount of repulsion between the remaining electrons. So if I reduce the repulsion, does that mean you get more or less attraction if you have less repulsion?
Less.
Less repulsion means more or less attraction?
More.
More, because they're opposites, all right? So if I have less repulsion, then I can have more attraction. And more attraction means I'm going to pull in tighter and be smaller. So the Fe2 plus cation only lost 2 electrons, but the Fe3 plus cation lost 3. So which one is going to be smaller, 2 plus or 3 plus?
3 plus.
3 plus is going to be smaller. So the Fe2 plus cation is larger than the Fe3 plus. So what that looks like here is if you have iron and you have iron 2 plus and you have iron 3 plus, right? They all have 26 protons. And the regular old iron has 26 electrons. Fe2 plus only has 24 electrons, and Fe3 plus only has 23 electrons. So that means that they look like this, right? With regular old Fe being the biggest, and Fe3 plus being the smallest, and Fe2 plus in between, because it all factors in here with these numbers of protons and electrons. 26 and 26 are balanced, but 26 and 24, well, that's going to pull in that way. And if I have even less, you can imagine it's pulling in even more that way. So all of that's to kind of help you look at that. Anions. So anions will always become larger than the original atom. And that's because my added electrons are all going into the same energy level. They are filling up a shell, okay? We kind of know what charge something is going to have because the whole point is looking at how many more electrons are required to fill up the shell. Fluorine only needs 1, so it's a 1 minus. It adds 1. Oxygen, well, it's got 6. It needs 2 more. It's going to take in 2. So the whole point of becoming an anion is to fill a shell. So adding those electrons are going in and filling a shell. These additional electrons provide increased repulsion. And if we remember that repulsion and attraction are opposite, if I increase my repulsion, I decrease my attraction, and I am pushing all of the valence electrons even farther away. All right, so they're all kind of pushing out. So there is kind of a weird thing, and it's not a whole lot, but it is a little, that if you look at all of these anion sizes, you will see that the 2 minus charge is actually always bigger than the 1 minus charge. Always. And it's because I've stuck 2 things in it. So I've got extra repulsion. So a trend is seen where a larger anion charge means there is more repulsion and a larger anion size. So a -3 is always going to be bigger than a 1. A 2 is always going to be bigger than a 1. A 3 will always be bigger than a 2 because it's got more electrons, more repulsion. So the last thing to look at here is comparing what is referred to as an isoelectronic series. I used that term before, but you may not remember it. Anybody remember what isoelectronic means?
No.
Yeah, that's totally fine. Iso is a prefix that means same. So these are the same number of electrons. All right, so when you've got a bunch of things that all have the same number of electrons because they've got their various charges. So if you have an isoelectric series, all having the same number of electrons, cations are always smaller, anions are larger, and the higher charge on the cation is even smaller, and the higher charge on the anion is even larger. So I've written out an isoelectronic series here. And first off, I want to write down the number of protons. So aluminum, 13, magnesium, 12, sodium, 11, neon, 10, fluorine, 9, oxygen, 8, and nitrogen, 7. But their number of electrons, if you pay attention, if I had 13 protons and now I'm a 3 plus, Well, I've got 10. 2 plus, I've got 10. 1 plus, I've got 10. Neon just has 10. Fluorine, 1 minus, I add 1 on, 10. Add 2 on, 10. Add 3 on, 10. So that's what I mean by isoelectronic. They have the same number of electrons. So if you think about it, if you draw an arrow to whichever number is bigger, it will tell you, do you get bigger or smaller? So 13 is bigger than 10. So I get much smaller towards the nucleus. 12, well, that's smaller. And 11, well, that's smaller. 10, those are equal. 9 compared to 10, well, that's a little bit bigger. That's bigger, and that's bigger. So if you think of it that way, that shows you that nitrogen, while it has the fewest protons, actually is the largest of all of those in that series. And then oxygen, and then fluorine. And the smallest is aluminum, because aluminum's got the highest nuclear charge, so it's got the most attraction, okay? Most attraction in. Okay, so everything that we're talking about for this week and next week, it can all be based on this notion of attraction. You're gonna have to be thinking attraction, attraction. Where is the larger amount of charge? Am I pulling in? Am I repelling away? What does that mean? So today was just talking about size. And then we'll talk about things other than size on Thursday and a Tuesday of next week. So if you need a picture of that, take a picture really fast, because I'm going to switch back to my slide deck. All right. And of course, this is all being recorded in case you missed anything or you want to look back later. Okay, so for Sunday of this week, you need to do Edpuzzle video 34. It opened yesterday. It's on periodic trends. It's just me going over some stuff on a website. You need to fill out the exit ticket on the next screen. And then this week, your completion grade is the periodic trends concept builder. The 3 levels go over 3 different trends. So the first level is atomic radius, which we've done today, but the other 2 levels are what we're going to do on Thursday. So you may not be able to like actually do this until after Thursday's class. Although if you watch the video on periodic trends, you'll probably be able to do the concept builder. But that's another thing where do it, get your 3 trophies with your stars, take a picture, attach it to the assignment. And then your actual graded assignment this week is the Google Doc that's in Google Classroom. It is a combination of multiple choice questions and then some things where you actually have to provide some explanations. You can get started on that assignment now and answer the questions based on atomic and ionic radius. And you want to make sure that you are that you're using these sets of notes to help you write your explanations. So the last thing I want to talk about really fast is next week. We are going to have class just on Tuesday next week. And I did actually assign stuff for you to do next week, but it's less than normal. So there is a video 35. It is already open. So once you watch video 34, you can go ahead and watch video 35, which counts for next week. In addition, you will have another Google Doc assignment for next week. The assignments in Google Classroom are actually going to open tomorrow. So you will see the last set of assignments for this week and next week, all in Google Classroom. I have put everything into Aspen so you can see what's there. One of the things I'm going to do with the rest of my time this week or today is go through and see what people are missing, even if it's just a single exit ticket or something like that. And I'm going to send you emails with direct links to anything you need. So a missed quizzes or an exit ticket or a video for a missed class or anything like that to make it easier for you to get caught up. And I will also let you know what your current grade is, and if things ended like literally today, what your overall course grade would be, so that everybody kind of knows where you stand and to hopefully reduce some stress. There is extra credit this week and next week, both free response questions on Flipgrid, just like before. And there is your exit ticket. Let me drop it into the chat. And so there it is in the chat. So make sure you do the exit ticket, because you lose a point if you don't, and that's dumb. And that's it. If people have questions, you can hang out. Otherwise, those of you who are taking your AP Psych test later, good luck, and I'll be around later. Class is over. Bye-bye.
Bye, Miss Baskin.
Bye.
Bye, Miss Baskin.
Bye.
Miss Baskin.
Is